Okay, so we are going to be talking about exponential functions. Now, what is an exponential function, or how do we define it? Okay, first, we are going to define a number that we're going to call b. This number is going to be larger than 0 and different than 1. The exponential function y equals f of x is a function that has the form b elevated to the x. Okay, so we've got our number b, and this number b again is larger than 0 and different than 1. And so f of x is going to be b elevated to x. Okay, so now the x, the dependent variable, is the part of the function where the exponent is. So b is going to be called the base, and x is going to be called the exponent. Okay. For an exponential function, the domain is going to be all of the real numbers. So what does this mean? We can actually provide any value we want here of x, and there are no restrictions. Okay. So for the exponential function, the domain is always going to be from minus infinite to infinite. We can put any value there to x, and it's going to be valid. Remember that we've got a few restrictions that we had been talking about previously with regards to domains. And that was if I have an even root, what's inside the even root cannot be negative. That's a restriction for the domain. And also, if I have an expression that has a numerator and a denominator, the denominator can't be 0. Those are the restrictions that we have been working on. And there's going to be another restriction that we're going to add when we're going to be talking about logarithms. But right now, for the exponential function, there is no restriction in the domain. So it goes from minus infinite to infinite. The range, however, is going to be from 0 to infinite. And why is that? Well, first off, if we notice here, if b is any real number that is larger than 0 and different than 1, and I elevate that to any another real number, then in this case it's going to be x, that can go from minus infinite to infinite. First off, I'm never going to be able to generate a 0 here. Okay, so if I have something elevated to a power, I'm never going to be able to generate a 0. This is why the interval here at the 0 is open. The other thing is that I'm never going to be able to generate a negative number. So if I've got a number elevated to a power, and that number by definition is larger than 0, is positive, then I'm never going to be able to generate a negative number. And so this is why the range is going to be from 0 to infinite. Okay. Okay, let's move on. Okay, and so there are some laws of the exponents, and this shouldn't be new to any of you guys. In previously, you should have had a math course where you talked about the laws of the exponents. And actually, we use these laws of the exponents regardless of if we're talking about exponential functions. And basically, what are these laws? Let's just go through them and refresh our memories here. But if I have two exponential functions that are being multiplied, or I've got two mathematical expressions that have exponents and these are being multiplied, then what happens is that in the resulting expression, the exponents are added, okay? So if, for example, I would have 2 elevated to the 3 multiplied by 2 elevated to the 2, we've got the same base here. In this case, the base is 2, or b equals 2. And so the result here would be the same base, which is 2. I'm sorry, and the exponents are added, which would be a 5. Okay. The same thing happens if, or something similar happens, I'm sorry, if the mathematical expressions are in a quotient or one is being divided by the other. So here what happens is that the exponents are subtracted. So for example, if I have 2 elevated to the 5 divided by 2 elevated to the, I don't know, 3, then what we're going to have here is the same base, which is 2. 5 minus 3 is 2. So they are subtracted. And again, in this example, 2 is the base. Okay. The other is that if I have 1 divided by an expression that has an exponential, that's the same as having the base elevated to the negative of the exponential. And this is actually very simple to demonstrate. So if I, for example, have 1 divided by 2 to the 3, then actually what's happening here, or this is equivalent to 2 elevated to the 0. Why is that? Well, there's another law of the exponents which is important here to mention. And that law of the exponent says that anything that's elevated to the 0 is always going to give me 1. So 2 elevated to the 0 is equal to 1. Okay. And then I've got this divided by 2 to the 3. So what happens there? If I use the second law of the exponents, then it's going to be 0 minus 3. This is going to give us 2 to the minus 3, which is what we were saying. If I have the base elevated to an exponent and it's 1 divided by that, then that's equivalent to having the base elevated to the negative of the exponent that I have. A few other here laws that are important. If I have a mathematical expression with an exponent that's elevated to another exponent, then the exponents are multiplied. So for example, if I have 2 to the 3, and this is elevated to the power of 2, I'm going to use another number just to be to the 5, then what's going to happen here is that 2 to the 3 elevated to the 5, the numbers are going to multiply, and this is going to be equal to 2 to the 15. Okay, and here, sorry about that, just to be congruent again, for these examples, the base b equals 2. I'm just using 2 as the base just to use the same number, but we could use any number, any real number that's larger than 0 and different than 1 as the base. Okay. Now also, if I have 2 numbers that are multiplied, so for example, I've got a multiplied by b elevated to the exponent, then the exponent is going to be added to each of these. And the same thing happens if they're being divided. So for example, if I have 2, or 2 multiplied by 3, for example, which is 6, elevated to the power of 4, then this would be equal to having 2 elevated to the power of 4 multiplied by 3 elevated to the power of 4. And we actually, if we do that mathematical operation, we're going to get exactly the same thing as 6 elevated to the 4 is the same as 2 elevated to the 4 multiplied by 3 elevated to the 4. And the same thing happens over here if I were to have 2/3 elevated to the power of 4, then this would be equal to 2 elevated to the power of 4 divided by 3 elevated to the power of 4. Okay. And lastly, the other 2 properties here that are important is that anything elevated to the 0 is equal to 1. So always, if I elevate to the power of 0, it's always going to turn into 1. And also, anything elevated to the power of 1 is itself. Okay, so b to the 0 is 1, b to the 1 is b. Okay, that kind of sums up the laws of the exponents, which again, these shouldn't necessarily be new to you guys, and it's something that we commonly use when we have operations where we've got exponents. Okay, now the graph of an exponential function. This is important. The graph or the model of an exponential function has a very characteristic representation, and it's this one that we have here. So, but it's important to note a small detail here with regards to b. So for this is the graph of the exponential of a function. Notice that a very important characteristics of an exponential of a function, it starts off with very small values, very close to the x-axis. Remember that it's not going to cross the x-axis because we can have negative value. The range doesn't have negative values of y. The range is from 0 to infinite. So it starts off here very close to the x-axis with very small values. And then it starts increasingly growing when it crosses the 0 of the x-axis. And for 0, this is an important, for 0, the value is going to be 1. And we just mentioned that as a property. When x equals 0, or we elevate it to the 0, the value is going to be 1. And then what happens is that it rapidly grows, And this is one of the important characteristics or applications of exponential functions. You've probably heard of the term exponential growth. What does exponential growth means? It means it's a growth that starts off with a very small rate, and then boom, it starts going up very quickly. Exponential growth is different than linear growth. The linear growth is a growth that has a constant rate. With the exponential, it doesn't happen that way. With the exponential, it's a growth that starts off small and then boom, it goes up. This is the graph for the exponential function when b, okay, is larger than 1. Okay, so this means that the graph here, b is 1, 2, 3, 4, 5, 6, 10,000, 15,000, whatever. It's a number that's larger than 1. That's very important. Now, look at this graph over here. This graph over here is also the graph of an exponential function, but what do we notice? The graph is reflected, and it has an inverse behavior. It starts off very, very, very large, and then starts decreasing very slowly until it kind of tries to reach 0, but never does. Here also, the important is that the crossing point is still, for x equals 0, the value of the exponential function is 1. That's the same thing as if I elevate to 0, I'm going to get a 1. But the characteristics of this graph is the inverse. Why does this happen? This is the graph of the exponential function when b is between 0 and 1. Okay. So here, for example, this function that I'm graphing here on the left, b equals 3. So it's larger than 1. That's why it's increasing. But if b were less than 1, between 0 and 1, like 1/3, then it's decreasing. That's a very important characteristic of the exponential function. If the base is larger than 1, it's going to be increasing. If the base is between 0 and 1, or a fraction, then it's going to be decreasing. And we can have exponential growth, or we can have exponential decay. The first case is exponential growth, meaning that it starts off small and then goes rapidly upwards. And then we can also have exponential decay. Exponential decay means that, I'm sorry, the function is, the behavior, I'm sorry, is going to start off very rapidly, and then it's going to start at the end slowly decaying, but it's going to start decaying or going down very quickly. So those are the characteristics of the exponential graph, of the graph of the exponential function. And now these are just a couple of other examples. So we notice the blue graph is for b larger than 1, and the red graph is for b between 0 and 1. We see that both graphs are the same, but they're reflected. When b is larger than 1, it increases. When b is between 0 and 1, it decreases. The other thing that we can notice here is how does the exponential graph behave. For example, for b, if we increase the value of b, so we start off at 1.2, 2, 3, 5, and we start growing larger, the base, notice that when we start increasing the base, then that's equivalent to a stretch. So if the base increases, it's going to start getting closer to the y-axis. Or what does that actually mean? If the base increases or is larger, it means that the exponential growth is larger also, or quicker. Sorry, it's quicker. And so we notice that the graph for B for 1.2 is flatter than the graph for B when B equals 5. Okay, so we start making the B larger, and when the B gets larger, the graph starts getting closer to the y-axis. The same would happen for the inverse, or the negative. I'm sorry, when b is between 0 and 1, the same thing would happen when we start in this case decreasing or increasing the values between 0 and 1. Okay, now some properties of the exponential function, just kind of summarizing. The domain is going to be from minus infinite to infinite. The range is going to be from 0 to infinite. The y-intercept is in 0, 1, and it has no x-intercepts. And we notice this again. The y-intercept is going to be here in 0, 1, and it has no x-intercepts because the x-axis is an asymptote. It's always going to be close to the x-axis, but it's never going to cross. The function is increasing for b larger than 1 and decreasing for b between 0 and 1, and that's what we're saying. If b is larger than 1, it's going to be increasing. If b is between 0 and 1, it's going to be decreasing. The x-axis is the horizontal asymptote, so it's never going to cross the x-axis. It's continuous from minus infinite to infinite, so it's never going to have a break here. And another thing that's important here is that the function is 1-to-1. And we can test that using the horizontal line test. So if we do the horizontal line test, in any of the cases, either the red or the blue, these are two different functions. Remember, it's only going to cross in one point. Okay, same thing happens here. It's only going to cross in one point. And we have to remember, if the function is 1-to-1, it means that we can calculate its inverse. Okay. Now let's look at a particular case of the exponential function. And this is the exponential function using the number e. Now, what is e, or where does e come from? E is a magical number, actually. And it's literally a number that I said it's a magical number, but it's really a number in math that has very special characteristics in math, in nature. And E is this number here, and it's 2.71, 8281, 828459, et cetera, et cetera, et cetera. It goes on and on and on and on and on and on. An infinite number of decimals. Okay. Remember one thing when we were talking about numbers, this is an irrational number. And why is it an irrational number? Because, as we mentioned, it has an infinite number of decimals here, and it cannot be represented as a quotient of two real numbers. And E comes from a very important scientist mathematician who is called, I'm writing it down here before I pronounce it. Depending on where you're from is how you pronounce this. So in Spanish, we call him Euler, because we in Spanish, we pronounce all of the vowels as they are. In English, sometimes some people refer to him as Euler's number. But actually, if we're going to use the correct pronunciation, it should be Euler's number, Euler's number. And Euler, however you want to call him, he was a very important scientist mathematician that, among other things, discovered this number. And basically, it's a number that that the way it's mathematically defined is we have this function, this kind of weird function, which is 1 plus 1 divided by x elevated to the x. And so if we give that number, that function numbers of x, increasing numbers of x from 0 to infinite, we're going to notice that that function is going to tend to be this number, okay? And it has many interesting and important applications, again, in life and in math, in physics, and in life. And it's used to describe certain behaviors. And so for an exponential function, when we choose e as the base of the exponential function, then the exponential function turns into what we call the natural exponential function. Okay. The graphs of this function are exactly the same as the graphs for an exponential function, but the natural exponential function, the only difference that we have in the graph is that there are certain points here of reference. So if x equals 1 in the graph, then the number that we get is e. And also if the graph x equals -1, what we get is 1 divided by e, or e to the -1, okay? Same thing happens if e to the -x, remember that if e were a fraction, so instead of working with e, we would be working with 1 divided by e to the x. We mentioned that when it's a fraction, it's the same graph, but it's reflected. And so we've got 0, 1. In both of them, 0, 1 is still going to be the pointed crosses. But now we're going to have, for the value of 1 here, the function is going to be 1 divided by e. And for the value of -1, the value is going to be e. So the behavior is exactly the same as a normal exponential function, but there's a reference number there, which is e, or Euler's number. And so, as we mentioned, this function has some important properties that are reflected or used in a lot of fields. Okay. And this is kind of what I was talking about. Exponential models or functions have many applications in different in different fields. So basically, whenever I want to represent or behavior or try to understand a behavior in nature that is not linear, then we're probably going to have an application for exponential models or functions. So remember that a linear function is a function where the rate of change is going to be constant. So, for example, the rate of change is going to be constant. The delta x with regards to the delta y is going to be constant. Okay, but we're going to have other behaviors where the relationship between x and y, which is what we're talking about, is going to have a behavior that's either going to be growing, as we call it, exponentially, or maybe it's going to be decaying exponentially. And these are cases that need to be that cannot be represented with linear models. And so that's where we use exponential models. So some of the applications of these are population growth. Okay. So the growth of a population isn't necessarily linear. Okay. Carbon dating is another application. So we use this to approximate the age of fossils. Laws of cooling and warming. When something gets heated or gets cooled, it doesn't necessarily get heated or cooled with a constant rate. So temperature differentials are used here. And also in finance, compound interest, for example, and some other financial applications are used here or examples of exponential models or functions. And so one interesting example of this is what we're seeing here with regards to the spread of a virus, for example. So if we were to be talking about the spread of a virus, and I'm going to try to explain this here with a couple of drawings here. Let's see if this works. So imagine that I have one person here. So I have a population, and I've got one person here that is infected by the coronavirus. Any virus. Let's not talk about coronavirus. And so this person now is in contact with two people, or one person. Let's say that he or she is in contact with one person. So now this person is also has a contagion. But then this person here is in contact with two more people. And so now these two have a contagion. And now let's say that this person was in contact with three more people. This person, let's say that he or she is in contact with two more people. Suddenly what happens here? Now there's more infected. So how many infected did I originally have? I had one, then that one turned into two, then that two turned into 1, 2, 3, 4. Then that 4 turned into 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you notice that the behavior that we're seeing here isn't linear? So if we were to graph this behavior, okay, as time went on, we had 1, 2, 3, 4, and then we had, for 1, we had 1, then for 2, we had 2, and then for 4, I'm sorry, for 3, which is the one we had here, 1, 2, 3, 4, 5, 6. For 3, we had 6. And then for 4, when we added this one, now we've got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is kind of an ugly graph, but notice what's happening here. Okay. Let me try to mark that a little bit more. Let me just do this here. So this is just kind of a rough drawing here. So notice what's happening with the behavior. The behavior isn't linear. It's starting to be a curve, and it started out very slow, and then it drastically got larger, and so on and so forth. We could keep drawing a graph of this, and this is kind of an example as to how a virus can spread. And this is an example of what we call exponential growth. It started off very small, and then suddenly it starts getting larger, and it starts getting larger quicker. Okay, clear these drawings. Okay, so that's kind of a summary here of exponential functions and models and their applications. And so the next thing we're going to do is that we're going to solve some problems.